The equals with the special equals, the sim equals, the special equals that we've been having for the whole Lebesgue chapter with this A and B. And then we have this almost everywhere thing, which was introduced last time. And both of them are limits, right? Every time we write sum of n equals 1 to infinity, we mean the limit as n goes to infinity of summing up the first however many. So I guess n equals 1 to m, and take the limit as n goes to infinity. So this is an almost everywhere limit, and then this is some kind of special limit that we talked about. And they're related. They are related. We talked about how they're related. But in what way are they related? Which one implies which one? Maybe they both imply each other. What is going on? And so that's what I want to do to start with. Okay, I'll give you a minute to work on that. Any questions or comments while we're working on this one? Okay, let's do 1 minute here, and let's see how we do. Okay, let's see what people said here. Which one implies which one? Let's see what people said. All right. "12 people answered. Some people selected both. That's why the sum of 6 plus 9 is more than 12. 6 people said the special one implies the almost everywhere. If you have the special one with the sim equals, this is sim equals in LaTeX, tilde equals. If you have the special one we've been doing in our definitions, then you have almost everywhere. 6 people said that. And 9 people said the opposite. If you have almost everywhere, then you have sim equals. So majority of people said almost everywhere implies sim equals, and that is wrong. So if you were one of the 9 people that picked this, you are wrong. This must mean you don't understand the definition. So here's what I want to do. Go back to your notes. We're going to take 2 minutes here. Go to your notes, find this definition. This is the most important definition in chapter 2. We've used it in every single class. I guess we didn't use it right at the beginning when we were doing step functions. Maybe I even wrote it on the board, I think, to say this is why we're doing step functions. Go back to this definition, check this definition, and then compare it. Now that you know almost everywhere, compare it to almost everywhere. In what ways are they the same? In what ways are they different? And why did most people get it wrong? Okay, so take 2 minutes, think, look up your notes, and then we will discuss. people have stopped talking, so maybe we can end the timer a bit early. Let me get the notebook or the blackboard out here. Okay, here's the blackboard with some silly probability stuff. Okay, and we want to do this. Okay, so the first thing we're doing, oh dear. We are comparing almost everywhere versus, okay, who can tell me what's the difference? Why are they different? Yeah.
Well, for almost everywhere, there are some points at which the two functions are not equal.
Okay, that's very good. So almost everywhere is exactly, AE is almost everywhere. And almost everywhere gives you one of these weasel sets, okay? Where we're saying like, something is true, except for there's this like little bad set over here, and you don't need to worry about it. So you're like, you know, it's like when you're telling someone and you're like, look, I definitely know that this happens all the time when I fight with my wife. I'm like, I'm 100% sure that this happens, and then it turns out I'm wrong. I'm like, oh, except for that event, right? That was a 0% chance. So it's like you're like committing. You're like, yes, it's absolutely happening, except for sometimes when it doesn't. Okay. So f equals the sum of n equals 1 to infinity of fn almost everywhere means the limit as n goes to infinity of fn of x equals f. Okay, except I don't want the actual function. I want the sum. So we do m to infinity of the sum of the first m equals f, except for some bad set, x in B, and B is a null set. B is a null set. So that's what almost everywhere means. You have this little null set. What do we know about null sets? The integral is 0. Or there's a 100% chance that the null set doesn't happen. There's a 0% chance the null set happens. So except for some tiny set, the limit is this. So it's like pointwise convergence, except not everywhere, almost everywhere. Okay, very good. What about the sim equals? Because this one had something similar. So in what ways is it the same? Yeah.
It's equal for all the points that the sum is finite.
Yes, very good. Okay, so on the other side of the wall over here, right? We have the limit as m goes to infinity of the sum from n equals 1 to m of fn of x equals f of x, except for x in B, and this time B is not just any null set. Like for almost everywhere, B is any null set. That's the condition. So this is the condition for almost everywhere. B is any null set. But in this one specifically, B is the set where the sum of n equals 1 to infinity of the absolute value of fn of x equals infinity, the set of x values such that this. So B is like a specific bad set. So over here, when we say almost everywhere, we're like, there is some null set, so this thing works. Okay, so we have our weasel set where we're like, it works except for some set. And we don't even say what set it is. We're just like, it's some small set, don't worry about it. Okay, over here we're like, very specifically, it is this set. Okay, so what is the relationship between these two things? The specific set and some arbitrary null set. Well, it turns out, and this is something we proved a while ago, I think it was right before the break, which is maybe why people are a little hazy on this. This thing, it turns out, is a null set. This thing is a null set. So fact. This B, maybe I should give it a name. Let's call it B sub Fn. It's the bad set of the Fn's, okay? B sub Fn is a null set, is in fact a null set. There is a very kind of silly proof why it's a null set. Does anyone remember the idea of why this thing must be a null set? And it starts with, okay, we had f is equal to all this stuff, f1 plus f2 plus ... And it turns out f plus the indicator of b sub fn is also equal to this stuff. When you add on the indicator of the b sub fn's, most of the time you're adding on 0. The only time you have changed the value of the function is when these things add up to infinity, and that it doesn't count. That's our weasel set. We don't look at that set. So this thing and this thing, they are both sim equals the same sequence, and therefore they must have the same integral, right? Therefore, the integral of f equals the integral of f plus the indicator of this bad set, and therefore the indicator of this bad set must have integral 0. 0 equals the integral. So that was the proof. That was in a Tuesday, Thursday video a few weeks ago. So it turns out this thing is a null set, and therefore, if you have sim equals, you definitely have almost everywhere, because you have it on a specific set. On the other hand, if you have almost equals, it might be something other than the set, and it doesn't go the other way, right? So this is like some arbitrary set, null set. This is like this specific null set. So that's very important. There is one other reason that almost everywhere convergence does not imply this. So this thing is one reason, but there's another reason. Yeah?
The tilde equals also has condition A, which
That's right.
is completely irrelevant.
Yes, so condition A is an extra condition, and condition A also says, so condition A also says must have the sum of the integral of the absolute values of the Fn. That must be finite as well. And almost everywhere definitely does not include this. Okay. If you remember, this tilde equals was what we built our whole integration on. We write a function as tilde equals sum of step functions. And this condition was crucial in proving that they converge and settle down, right? Remember we had like monotone convergence, like we said if the functions are going right down to 0, then it works. And then this was like we can approximate a sequence by a monotone sequence by replacing the functions with their absolute values, and this made sure that it was okay. So that was a crucial thing. Okay, so this is very important. And I'll give you an example. On the quiz, a ton of people got this question wrong. They said the indicator of a null set is sim equal to 0 plus 0 plus 0 plus 0. And this is false. This is a false statement. False. And the reason is the set where these things converge. So this thing is almost everywhere equal. Let me write that down first. True is that the indicator of a null set is equal almost everywhere to 0 plus 0 plus 0, but it is not tilde equals. And the reason is they're equal almost everywhere, but this set, the bad set for all the zeros, is everything, and that is not necessarily the bad set for the set B that was given. So they're equal almost everywhere, but they're not equal on the specific set, and that set turns out to be everything, right, where they're supposed to be equal, and they're not. So that's why I wanted to mention this. And also, the topic of today's class is almost everywhere convergence versus convergence in norm versus L1 convergence. And those are the two things that we want to compare and contrast. So if you're mixed up on what is almost everywhere convergence, then the class won't make any sense. Okay, questions or comments about this idea? Yeah?
When we defined tilde equals, I think the sequence also specify that the sequence has to be either step functions or integrable functions?
Yeah, that's true. So we started with step functions. And then we proved that that made sense. And then we built up to integrable functions, and we proved that it still made sense, and you don't get something new. So after now that we've done it for both, we can write it with any type of function, but it's true they have to be integrable, otherwise like this kind of statement makes no sense. You can't, like, what does it mean if the sum of the integrals is finite if the integrals aren't even defined? So it's true they have to be integrable functions. Yeah.
Yeah, so almost everywhere it doesn't have to be integrable, right?
That's true, almost everywhere it doesn't have to be integrable. Okay, yeah, this is another argument for this one does not imply this one, right? Because maybe these functions aren't even integrable at all, and then it's not even possible that they could tilde equals converge. That's a good point. Yeah. Yes.
This is going to sound like a stupid question.
Those are the best kind of questions. Yeah.
I'm kind of having a hard time grasping why tilde equals implies almost everywhere. Like, if we have tilde equals, it means that it converges except for the one specific bad set.
Yes.
But then what if it converges on a different bad set and then almost equals wouldn't apply? Isn't almost equals for every bad set it doesn't work? Or
That is a fantastic question. Very good. Yes. You're thinking about it in the right way. Almost equals means there's one bad set out there in the universe. There exists a bad set where it happens.
oh.
Okay, so this is very important. Yeah.
It's all bad sets.
Yes, no, this is it's for all versus there exists. You're absolutely right. It's not for all bad sets. It's there exists a bad set. And of course, if it was for all, the implication would be the other way, but the definition would make no sense. So this is extremely important, and I was too casual about this. Let me say it. Almost everywhere means there exists a bad set B. Yes, absolutely. Bad set B, such that, okay, and so this is important. When they go almost everywhere, there is some bad set where this is a true statement. And, different people can find different bad sets. If I prove almost everywhere and you prove almost everywhere, maybe my bad set is bigger than your bad set, and you did like more work. Like you proved it converged even for some points in my bad set, but that's still fine, as long as they're both null sets. So this is very important. It's that there exists. Yes, fantastic question, and I can see why there was confusion. I was a little bit casual about this, and it's important. Yeah.
Maybe I've just forgotten how that quiz question was set up.
Yeah.
That's the problem.
Mm-hmm.
But what do you mean that the bad sets might not be the same for like on either side, and that's why?
So the bad set for 0 plus 0 plus 0 plus 0 is nothing, right? The specific place where the sum is infinity is nothing, because nothing, you never add up zeros and get infinity. And then in the quiz question, this was just an arbitrary null set. So this is let B be an arbitrary null set. Okay. Right, and so this thing is equal to zeros almost everywhere because B is a null set. So the difference between this and this is just the indicator of B, and that's a null set. So these things are equal almost everywhere because their difference is a null set. But these things are not sim equals, they're not special equals because they're supposed to be equal everywhere, and they're not equal everywhere. They're only equal on the complement of B.
Oh, okay.
Okay. Yes. This is like important to think of. Yeah. And basically, there's like this notation, this sim equals notation, has a lot of stuff wrapped up in it. It's easy to kind of like think it's just equals, but it's equals plus some special stuff, and don't forget the special stuff. Okay. Yeah. Great. These are really good questions. Anyone else? Okay. So now we're going to talk about almost everywhere convergence versus L1 convergence. And almost everywhere we've talked about for a bit now. I'll remind you, L1 convergence means like convergence as integrals, right? So this is like we were doing in chapter 1. We have the norm, the L1 norm of some function we know now is the integral of the absolute value. And we say Fn, let's say it converges to 0 in L1. And by 0, I mean the 0 function. I'll write 0 vector. So remember, it's the 0 function. Means the integrals are going to 0. So the integral of the absolute values of the fn's converge to 0. And actually, So they converge to 0, the number. Okay. Right? So for functions to converge to 0 in L1, they must have integrals that are converging to 0. Whereas almost everywhere convergence just is the kind of pointwise limit. Fn of x is converging to 0, the limit as n goes to infinity. So there exists bad set B such that this happens except for x in B. Okay. And B a null set. B a null set. Yeah. So usually I think of the bad set is the set where the things that you want to happen don't happen, and we're saying that that set is a null set. That's really what almost everywhere convergence means. Okay. And so the first most important thing that you must understand, absolutely crucial, these things do not imply each other. They're not the same. You would think they're the same, kind of like casually, if you're like a calculus 1 student. You're like, oh, if the function is going to 0, the integral has to go to 0. Like, what could happen, right? But very important, no, they are not the same. They are different. So this is the most important fact number 1. Fact number 0, I don't know, fact 0. Fact 0. They are not the same. Not the same. Okay. And we kind of saw some examples of stuff like this in chapter 1 already. That might jog your memory on what's going on. And so e.g. in chapter 1, we had sequences that were going to 0 pointwise, but their norms were not going to 0. We had, and I think the best example is the sequence en, which is the sequence of all zeros except for 1, 1 in the nth slot. And then it's all zeros after that. And this is an element of little L1, right? Or various sequence spaces. And En is going to 0 for every component. But the norm of En is always 1. It's not going to 0 in norm. So En of I goes to 0 for every fixed I. But, so for all I, a natural number, En of I goes to 0. But the norm of En is always 1, which is not going to 0. So it's not going to 0 in the L1 norm, but it is going to 0 pointwise. And this is the kind of example that will also work for functions. Does anyone remember? Yeah.
I just want to clarify something.
Yeah.
Are the functions, they're defined on like a interval?
Well, so technically they're defined on all R,
Okay.
but all the functions we do, I think, end up actually being on an interval.
Okay.
So if it helps you to think on an interval, that would be fine. Yes. Okay. Other questions about this example? So let's do some examples like this in L1. So now we're going to have similar examples in L1 of R. Okay, and here is the one example I really like. And actually, okay, let's not even do L1 of R. Let's do L1 of 0, 1. So a function defined on 0, 1. Because it's not really the R that's the messiness. It's the fact that functions, the real number line has sort of infinitely many points. And there's lots of places to hide, right? You can sort of cram infinitely many things into this little 0, 1 interval. And so here is the function that I'm going to do. I'm going to do the function fn, which is the indicator of 0 to 1 over n. And I think let's do it open and close, so it's a step function. 0 to 1 over n. So this is, we've seen this one before. This is the sort of sliding spike getting crunched down. Sort of in your brain looks like this. So it's over here, and this is an interval of length 1 over n. And this thing is going to 0 almost everywhere, because for any fixed x point, eventually the spike passes you, and then you're 0, right? We've done this one a few times. Now, as written, the integral of fn is 1 over n, and 1 over n does go to 0. So this thing goes to 0 almost everywhere. In fact, it goes to 0 everywhere, literally everywhere, and its integral also goes to 0. But you can easily modify it so that the integral does not go to 0. So right now it goes to 0 almost everywhere because the spike eventually passes you. The integral is 1 over n width times height 1, and 1 over n times 1 is 1 over n. That goes to 0. So it goes to 0 in both ways. But we can easily modify it so that it still goes to 0 almost everywhere, but doesn't go to 0 in norm. Yeah?
You just multiply it by n.
You multiply it by n. Exactly. Very good. So, and I think we did some examples like this as well. If you make the height here, if you make it n instead of 1 over n, now the area is always 1. And so it's still going to 0 almost everywhere, because for every fixed point, eventually the spike passes you, and you're equal to 0. But now the integral of fn equals n times 1 over n, which is 1. And so it's not going to 0. And in fact, you can make it even worse. If you want to make it even worse, you could put in an n squared. So if you want, you could do n squared times 1 over n, and then the integral would be n, which is going to infinity. So it is up to you how bad you want to make it. But in any case, you can cook it up so that it doesn't go to 0. So this is a really important example. One of the ways in which almost everywhere convergence can not imply integral convergence is if the height of the function gets really, really tall on some really, really tiny set. And then you have almost everywhere convergence because the tiny set sort of like misses everything. But it's really, really tall in that one spot. And then that causes a sort of like infinity times 0 situation. And you end up with something whose limit is not 0. Okay, so in this case, let's say it's not equal to 0, or it's not going to 0. That's the important thing. So this is the moral of the story. The moral can have a big spike, let's call it big tall spike on a shrinking set, shrinking to nothing set. And the big tall spike times the shrinking to nothing is kind of like an infinity times 0. And it can work out that the infinity is bigger than the 0. And the integral of fn will be, okay, I'm going to put this in quotes. Don't tell the math, please. Infinity times 0, which is not going to 0, okay? We can put it in quotes so you don't get arrested. Okay, there we go. All right, so this is the moral of the story. That's one way. Are there questions or comments about this example? You might think, okay, this is like very silly. Like, does this ever matter in real life? And I'm going to tell you an example where this matters in real life. And it matters when you go to the casino, okay? So imagine you are going to the casino. And when you go to the casino, there's all sorts of interesting characters, let's say, at the casino. And one of them might say to you, listen, I have this betting strategy, and this betting strategy never loses, okay? And this is called, some people call this the martingale betting strategy. Betting strategy. Who has heard of the martingale betting strategy? Okay, a few people. Let me tell you what the martingale betting strategy is. Very simple. So you go to a game at the casino. It has to be a 50-50 game. Real casinos don't have 50-50 games, but let's pretend this casino is very nice and they have a 50-50 game where you can bet like on a coin flip, heads or tails, and you win double your money. So take a 50-50 game. Something like blackjack is pretty close to 50-50. All right. And what you do is you start by betting $1. You bet $1. And two things are going to happen. Either you win or you lose. You win, so 50% of the time you win, and you win $1. And 50% of the time you lose. And when you lose, now you're at negative $1 because you started with your dollar, you lost your dollar, now you're at negative $1 relative to where you started. If you win, you're at plus $1. If you lose, you're at minus $1. Most people would say, okay, great, sometimes you lose, sometimes you win. But the martingale betting people are like, aha, here's the strategy, okay? Here, now, if you lose, just bet $2. Bet $2, okay? Double your bet, because now if you win, you were at negative $1, but you won $2, so now you're up $1. So you're up plus $1, okay? And that happens if you win. See, great strategy. Either you win on the first round and get $1, or you win on the second round, you still get $1. It's pretty good. Does anyone know what's the problem with this? Yeah?
Well, if you continue this down, if you were to lose twice in a row, you'd be down $3.
Oh, yes, exactly. Very good. Yeah. So this is the weakness. Someone will point out, they'll say, oh, but then if you lose twice in a row, now you'll be at negative $3. Okay, down. The martingale people, they have an answer to this. Bet $4, yeah. Okay. You just keep betting. Don't worry about it. It does not matter. Win. Now you're up plus $1. Okay. Nobody mentioned the hidden downside that if you lose again, now you will be down $7.
Just bet 8.
Okay, but you just keep betting. So the strategy is very simple. I'll put ... And the strategy is always double your bet if you lose. That's the simple way. Double your bet if you lose. If you lose, you double your bet. No problem. The observation is this big tree. You're going to have this big infinite tree. And there's here's a summary of what you could say, which is mostly accurate. 100% of the time, you eventually win $1. This is like a true statement. Like, because the probability of getting sort of, quote, infinitely many tails is 0%. Okay? So if you follow this betting strategy, 100% of the time you'll win $1. This is a kind of almost everywhere convergence. So this is how I would say it in English, and then in math class I would say it like this. Let's let fn of x be a function that represents my winnings. And the statement I'm going to prove, I'm going to set this up correctly. And more specifically, like fn of x is going to represent my winnings. But more specifically, fn of u, where u is a random variable, fn of u is going to be a random number, and it's going to be like how much I won or lost. And it's going to have the same probabilities as the tree if you calculate it. So fn of u is the random variable of how much I won or lost. How much you lost. Okay, 1. And a mathematical statement that is absolutely true, like no quotes or anything, is that the limit as n goes to infinity of fn of x equals 1 almost everywhere. Like you literally win $1 100% of the time. The probability that fn of u equals 1 equals 100%. And I guess I could specify $1 so that we don't mix up our dollars and probabilities. You always win $1 in the sense that in the limit, you always win $1. Okay, 100% true statement. There's a friend of mine in high school who tried this strategy on blackjack on like online blackjack. I think he got up to $512 once, and then he won, and then he stopped playing forever. So it's like, eventually, if you're down, you get down quite a lot of money. Okay, so it's true, you win 100% of the time, even for my friend who was at $500. He did eventually win. What is the problem, though? So why can't we go to the casino and do this? This seems like a good 100% thing. Yeah.
You underestimate how easy it is to get like a long string heads or a long string tails.
Yes, so like psychologically you're saying it feels like you should never lose, and you're saying in fact you do sometimes lose?
Yeah, you run out of money.
Yes, okay. I see. Okay, so this is one fact. So one is this 100%. This is a mathematically true statement. It really is 100% in the limit. One thing is you're eventually going to run out of money. So you can't actually take the limit as n goes to infinity. That's one problem. But there's another issue, which is the probability is kind of hiding something bad. Okay, so the probability you win $1 is 100%. But what might you care about other than the probability? Yeah.
How long it'll take you?
Yes, this is very good. How long it'll take you? So maybe you'll eventually win $1, maybe it takes forever. It actually turns out that like the rare streaks of when you lose a lot, there are few and far between. So actually, the amount of time until you win is not that long. Like, even if you've lost many times in a row, in the next 2 flips, that's how long you have to wait on average until you win. So how long you wait sometimes is a problem in stuff like this. In this one, it's actually okay. Yeah.
In games like blackjack, how do you bet money if you have negative money?
Oh yeah, okay. Well, when I say you have negative money, what I just mean is like relative to where you started. Of course, you need like a bankroll that's big enough. You start with $10,000, and then you you're down $7. That's what I mean. Yeah, yeah.
This gives you like positive EV if you already have infinite money, but at that point, then why do you care?
Yeah, this is great. Okay, you use the right buzzword, which is EV, which is what the cool kids call it. What is EV? Do you know what EV stands for? Expected value. Okay. Expected value. And you said this has positive EV, right? You're like, look, you win $1 100% of the time, must be positive EV. If you're winning $1 100% of the time, then on average you should get $1. But that is a false statement. That is a false statement. So the expected value of Fn of u is actually 0, and it's 0 even in the limit as n goes to infinity. Okay. So the probability, the almost everywhere, is converging. You're converging to a 1 plus $1 100% of the time, but on average, you actually make no money, 0. Okay, and this is why this strategy is bad. Well, okay, there's a number of reasons why, but it's not. You can't make something from nothing. You're not actually doing anything. You're just shifting around where the money is, right? And you will win $1 100% of the time, but sort of on average, you make $0. And this is exactly the situation that we're in because the expected value is the integral. This is the integral of the function fn. And this is always 0, even though fn converges to 1 almost everywhere. Even though. Okay, and the picture is literally the exact picture I showed you before with that spike function. The function fn of x, what is it supposed to do? Well, fn of u is supposed to be, it's supposed to be plus 1 with probability 1 minus 1 over 2 to the n. So in other words, unless you there's a 1 over 2 to the n chance you lose n bets in a row, right? So going back to this probability tree. So what's the probability you lose 3 times in a row? Well, you have to lose first time, second time, and third time, 1 over 2 cubed. Unless this bad thing happens to you, that you lose 3 in a row. Now you know why I call it the bad set, right? If that's happening to you, it really is bad, right? Okay, so the bad kind of event here is you lose n in a row. Unless you lose n in a row, you're up $1. And so you're supposed to be plus 1 with probability 1 minus 2 to the n. And otherwise, you are at negative 1 minus 2 minus 4 minus ... minus 2 to the n. And this happens with probability 1 over 2 to the n. You can do this sum. The sum is 2 to the n minus 1. Oh, I think I'm off, but let's check here. I think this should be a minus 1, and then this is correct. Okay. So we need to come up with a function that does this. And the function is very simple. Fn of x, it's going to be 1 minus, and then I'm going to do 2 to the n minus 1 on the set, on the set between 0 and 1 over 2 to the n. Okay, does this do what I want? 2 to the n. Okay, I want maybe 1 on the rest of the set. Yeah. Okay. So that's my function. Okay, it's not fn of x, it's just fn. And this looks like a spike. Okay, so it's a big spike over here. There's this tiny bad set that has width 1 over 2 to the n, and the height over here is 2 to the n minus 1. And then on the rest of the set, you are equal to 1. Oh, but it's negative. Let's flip it upside down. It's very important you don't mix up dollars with negative dollars, or you will go bankrupt quite quickly. Okay, negative 2 to the n minus 1. Okay, so plus 1. So it looks like that. Okay, so it's a big spike that is shrinking down to 0. Right? The width of the spike is 1 over 2 to the n. The height of the spike is 2 to the n minus 1, and it's shrinking down to 0. And then you have this little area over here where you are getting plus $1. So plus $1 over here, and then negative big money over here, negative 2 to the n minus $1. And the area of this thing is always 1. So it's converging to 1 almost everywhere for the same reasons as before. Eventually, no matter where you are on the x-axis, eventually this little spike passes you by. So even if you're sort of somewhere quite close here where you're quite unlucky, eventually it passes you. So you're plus 1 almost everywhere. But the integral is always 0. Fn goes to $1 almost everywhere. Goes basically everywhere except for exactly at x equals 0, but x equals 0 on its own is a null set. So that's fine. So 100% chance, the probability that Fn of u equals $1 in the limit as n goes to infinity equals 100%. You have a 100% chance of winning $1, but the average is 0. The expected value of Fn of u is the integral of Fn, and this is actually literally 0 for every Fn. And the limit is also 0. Okay, so this is an important example. It turns out there's a nice theorem. In this theorem, there's a whole theory of these martingales now, martingale theory, that says that no matter what betting strategy you use, you'll always have mean 0. So you can't, if some weird guy at a casino tells you, hey, just use this weird betting strategy, you can't, it will always have mean 0, no matter what you do, if you start with a mean 0 game. Of course, in real casinos, you start with a less than mean 0 game. The casino will actually take money away from you. So if you do some weird betting strategy, you might be even worse off. So be careful who you talk to at a casino. And this is why these kinds of sliding spike examples sort of come up in real life or maybe just in probability. Okay. Questions about this example or anything else we've talked about? Yeah.
This is what the Wall Street banks do, except when they hit that negative spike, then they just get.
Yeah, exactly. Yeah. So yeah, in like finance, they call this strategy. They call this type of strategy. They call it picking up pennies in front of a steamroller. Okay, so there's lots of like stock strategies where you're like, oh, I'll just like bet that like Apple will like continue to go up a little bit, and you can like pick up your little pennies and you're like, oh, look at all the stuff I'm doing. But then once in a while, you get crushed by the steamroller, and then you go bankrupt. And so on average, maybe it's 0, even though it seems like you're doing quite well. But you're right, yeah, if you have a ripcord, get out of jail free card, then this is a great strategy because you sort of limit how bad things can go. Yeah?
Can you do this with some parlays?
I don't know what a parlay is, but remember, no matter what betting strategy you do, it will be mean 0. So it's a really nice theory. Of course, see, the thing is this when you turn this into math, you have to formalize what it means to not look into the future. So if you're allowed to look into the future, you can make a betting strategy that's very profitable. Only bet when you're about to win. So you have to define what does it mean to not look into the future. There's something called a stopping time, which is formalized as this, stopping time. So a stopping time is a time at which you can tell whether or not you're there without looking into the future. And there's this thing called a filtration that keeps track of information as you go. So it's a whole interesting theory, and it formalizes this kind of stuff. I'm guessing a parlay is some version of this, and it would be also mean 0.
Probably
Probably
not.
not. Okay.
There's no like fixed odds, I guess. So just whatever you make it.
Oh, I see. If you want to change the odds,
Yeah.
I think as long as it's a fair bet, because you see the thing is you can simulate any odds using the coin flip. So if I want to make a bet that is like a 1 out of 8 bet, then I'll just bet on the next 3 heads in a row. You see. So this any fair game, no matter what the odds are, will satisfy this. Yeah. Okay. Is there another question here? Yeah.
Is the expected value like, after every, like how much money you have after every bet, or how much money you have by the time you give up?
That's a great question. Okay, so Fn means after n bets. So basically take the tree and cut it off after n layers. And I'm saying the average after n bets is always 0.
Right.
And the average when you lose will also be 0. This is a different statement, but it's also true. Sorry, the average when you stop. So let's write this down. So it's true that Fn of u is mean 0, and it's also true. Wait, no, this is the one situation where it's not true. Okay, let's leave it like this. Let me get for fixed n. For fixed n. So, and that means Fn is where you are after n bets. This is your profit or loss after n bets. Fn equals profit, loss after n bets. Okay. Yeah, let's leave it like that. Yeah, there's certain theorems that say under such and such conditions, you can also do f of t, where t is this random stopping time. But let's let it be fixed. Okay. Yeah, very good. So this is why this stuff matters. Is you want to like think about these things, especially in probability. It really comes down to this idea of, okay, when is almost everywhere the same as expected value? When is expected value the same as almost everywhere? In our class, we're stating it as integrals and almost everywhere, right? So L1 versus almost everywhere. Almost everywhere versus L1, you really want to know where they are the same and where they are different. Okay. And that is the topic. So this chapter is called, this is the last section we're going to do in chapter 2 before we move on to chapter 3. And it is, I think it's 2.8. Did I really not write down anything? Yeah, 2.8. And it's called Fundamental Convergence Theorems. Fundamental Convergence Theorems. That is the name of the chapter. And this is the last one we're going to do. Because after this, we're going to sort of know enough about the Lebesgue integral. We can do some interesting stuff with actual integrals and things. And basically, it's under, so Fn almost to f almost everywhere does not imply Fn goes to f in L1. But Fn goes to f almost everywhere, plus some other conditions, does imply Fn goes to f in L1. And this chapter is all about what conditions do you have to add on, what do you have to also check in addition to the almost everywhere to be sure that it goes in L1. And these are the kinds of things that we're gonna use, and they're super useful. So one example of the use of this thing, an example application, is we're going to prove that the Riemann integral, when the Riemann integral exists, the Lebesgue integral exists, and they are equal. And the proof, okay, I'm not going to give you the full proof, but the proof sketch, and I have it written down. So you can go read it once we've finished this chapter. You can go read this exact proof. Let me see. Theorem, this is in theorem 2.10.1, so we're not going to do it. But the idea is you look at the lower Riemann sums, and you look at the upper Riemann sums, right? So the Riemann sums, they sandwich the original function from above and below. You call the lower Riemann sums, call that L for lower, Ln. So there's some lower functions, they live below the function f. And then you have some upper functions that live above the function f, some UNs. And you prove that the Ln's and the UNs, they converge almost everywhere to the original function. So Ln converges to f almost everywhere. UN converges to f almost everywhere. And then by the other conditions, you check the other conditions. When the function is Riemann integrable, the other conditions will hold. And then you will get, so this is plus other conditions. And you will conclude that the integrals converge to. So the integral of Ln converges to the integral of f, and the integral of UN converges to the integral of f, and everything will be good. So this is the kind of application. And I think this is the most, if you're doing like actual analysis in the wild, this is like the only part of all of chapter 2 you will use is the stuff from this section, because you have these like theorems that say like, oh, okay, I can use the theorem to prove the thing that I want. We'll have some examples of that at some point. Okay, but that's one example. Okay, what is the first sort of condition? And actually, the first one you can guess. So first type of condition. So this is condition, helpful condition number 1. So if you have this condition and you have almost everywhere convergence, so Fn goes to F almost everywhere, plus question mark, then Fn goes to F in L1. There's one we've been talking about for a while. It's come up in a lot of things. I think it came up at the beginning of this lecture. Can anyone think of what is the special condition you would need to make almost everywhere turn into L1? Something that is a little bit nice. So remember, when we defined the integral, we started with step functions, and we said we have these step functions, and they're getting closer and closer to the function f. And then we said the integral of f is the integral of the step functions, right? So this is kind of saying when the step functions get close to the function f, right? The step functions are getting close to f. Then the integral of the step functions gets close to the integral of f, right? So the whole definition of the integral was doing this kind of thing, right? It was saying if they're getting close together pointwise, okay, except for the bad side, then the integrals get close together, and we can use that to define the integral. But there was one other condition we needed to make that work. Yeah. Condition A, exactly. It's the absolute summability condition. So condition A, the absolute summability. And I'll write absolute summability over here. Summability. So if you have absolute summability and Fn goes to F, then it goes to F in L1 as well. And very specifically, I will give you the statement of a theorem. Okay, yeah. So we're gonna build up to this theorem, but I'm gonna start with theorem 2.6.6, which says that if Fn is sim equals to not Fn, if F is sim equals to the sum from n equals 1 to infinity of the Fn, then F equals the sum from n equals 1 to infinity of Fn in L1 of R. Okay, so we're going to build up to the theorem that I said over here. Remember, this sim equals is almost everywhere plus a certain kind of absolute summability plus this special like set. And we're going to start with this one, and we're going to upgrade it to the thing that I wrote in condition 1. That'll have a specific title as well. I will remind you, this is important. I'll write this now. I won't write it for the other ones. But when I write f equals n equals 1 to infinity of fn, right? As soon as there's an infinity, this thing is some kind of limit. So this is not really saying f is equal to something. It's really saying f is the limit of something, right? So just reminder that this really means f equals the limit as m goes to infinity of the sum from n equals 1 to m of fn in L1. And this means the norm of f minus the sum from n equals 1 to m of fn is going to 0, right? So it's like epsilon delta, epsilon m with this norm, right? So just make sure you know what this means. Don't think that it really is an equal sign. It really is a limit. I could write it the other way if you guys want. If you find it confusing written like this, I can write it out the long way. But I think it's like when you're kind of thinking about the statements, it's nice to have it written in the short way. And then only when you need to, you unpackage and see what it is. Yeah.
Should it be an M on top of the sum of the red?
Yes, very good. Yes, okay, great. Fantastic. Yes, this should be an m up here, right? So you sum up the first m, and then you take the limit m goes to infinity. And this is a sequence of things in L1. What does it mean for a sequence of things to converge? It means the difference in norm goes to 0. Very good. Yeah, okay. Okay, let's do the proof. And the proof is like it really is just like taking stuff we've already done and just rewriting it a different way. Okay, the starting point is, let epsilon greater than 0 be given. So take any epsilon greater than 0. Find n naught such that the sum of the integrals starting at n naught to infinity is less than epsilon. This is by condition A. Right? So condition A is this absolute summability condition. When you have this, it's all good. The tail sums up to less than epsilon. I don't want it to be less than infinity. I want it to be less than epsilon. Right? So the whole thing sums up to less than infinity, which means that if you go far enough out into the tail, the whole infinite tail has to sum up to less than epsilon. Okay. Now, we have f was equal to f1 plus f2 plus ... And therefore, we can subtract some finite number of terms of 1 minus f2 minus ... minus fn naught, and that will be equal to fn naught plus 1 plus fn naught plus 2 plus ... Okay. So it's okay to subtract finitely many terms. And therefore, this was a theorem we had. Therefore, by the bound on the absolute value of the integral, I can even give you the theorem number. I cannot give you the theorem number because I didn't write it down. Okay, you can. So this was something we did. We said when you have something is semi-equal to something, the integral of the absolute value of this is less than the absolute value of the integrals of those. The integral of the absolute value of f minus f1 minus f2 minus ... fn naught is less than or equal to the sum from n equals n naught plus 1 to infinity of the integral of the absolute value of fn. This was, okay, I think it was 2.5 point something. Okay. But this is less than epsilon. Okay. And then this thing really is, this thing is equal to the norm of f minus the sum from n equals 1 to n naught of the fn. So what we've shown is that for every epsilon, there exists an n naught, so that this thing is less than epsilon. And therefore, since epsilon is arbitrary, the limit as m goes to infinity of the norm of f minus the sum from n equals 1 to m of fn equals 0, and therefore the sum from n equals 1 to m of fn in the limit is equal to m, to fn, to f. Okay, there we go. Okay, so very simple proof, just pushing around the things using the previous definitions. The upgraded version of this is to say, actually, theorem 2.8.1 is that the space L1 is complete. And this was a major theme in chapter 1, was when are things complete? When do sequences converge? And basically because of this sequence, right, we're saying as long as you have the absolute summability, things will be fine. Let me zoom out here if someone's still copying. Okay, that's what we're going to prove in 1 second. Yeah?
I think that is 1.5.2.
2.5.2, that sounds right. Thank you very much. 2.5.2, it says that when something is something else, the integral of the something is less than the absolute value of the integrals of the other thing. Okay. Okay, so we're going to prove it's complete. Again, this is not going to be a big proof. It's nothing complicated. Complete basically means every absolutely summable sequence is summable. So reminder, complete means, so it means every Cauchy sequence converges, but we prove that that's the same as every absolutely summable sequence converges. Sequence converges. And the theorem we just proved is basically saying, okay, as long as you have the condition A, which is the absolute summability, you will converge. And so it's going to be like a rearrangement of that theorem. Okay, so here is the proof of theorem 2.8.1. Proof. Let the sum of n equals 1 to infinity fn be some absolutely convergent series. i.e. the sum from n equals 1 to infinity of the norms of the fn, which are the sum of the absolute value of the integrals, is finite. And if we can prove that it converges to something, then we will have the completeness. Okay, there's another corollary we did. By corollary 2.5.4, if we set f to be this thing, f is equal to the infinite sum of the fn's, or 0, and it's this sum when the sum is finite. The sum, all right, is finite. And it's 0 when the sum is infinite. Let me write the sum of the absolute values. Let's just write it up. Okay. It's this when the sum of the absolute values is infinite if this equals infinity. And then it is this thing otherwise. So basically, add them up as long as this works. And corollary 2.5.4 says f is sim-equal to the infinite sum. Right? So basically, if you have condition A, you can always define f in this way, and then like you'll have the thing with condition B that you want by the way you cooked it up. Like it works exactly the way you want. Yeah.
I'm confused about why it's that it's equal to the sum when the absolute sum is infinity.
Yeah, well, basically, okay, remember, condition B is, okay, going all the way back to what we did, right? This condition, we want them to be equal except for when the thing is infinity. And I'm just defining a function that does that. So you give me the fn's, but you didn't give me f.
You're saying except for when it's equal.
Except for when it's equal. Did I write it down the opposite way? It's possible. So when the sum, yes, I have it backwards. Very good. Thank you. Okay. Yeah. All right. Yeah. Okay. If the sum is finite, then okay. Yes. Thanks very much. Okay. Okay. Let me fix this as well. Okay. So basically, we're cooking up. Like you give me the fn's, but you didn't tell me what the limit was. But I'm cooking up what the limit is point-wise, right? So for every point where it makes sense, I define the function f. Now I have condition A because of the thing you gave me. I have condition B because I cooked it up like that. And now, we did this earlier. This was corollary 2.5.4. You really have this. Yeah?
Just to is it absolutely convergent or absolutely symmetrical?
Oh, in my head, those are the same thing.
The same thing?
Well, we should see what the textbook says. But in my head, those are the same thing. It just means, as a number, the sum of the norms is finite. That's what they mean. Yeah. Okay, very good. So f is this thing. And the theorem we just proved says, now they converge. By the theorem we just proved. By theorem 2.6.6, that's the one we just proved. F equals the sum of n equals 1 to infinity of fn in L1. And therefore, we have the convergence we want. So you started with a sequence that was absolutely convergent, right? The sum of the norms was finite. We found its pointwise limit. F was tilde equal to its pointwise limit. And then by the theorem we just did, it converges in L1. Every absolutely summable sequence converges to something, this function f in L1. Okay, it's kind of not very surprising. And now I'm going to go and do the theorem that I promised you, which is theorem 2.7.12, which is this almost everywhere thing. So suppose only almost everywhere convergence. So forget about tilde equals. This statement has no tilde equals in it. Suppose the sum from n equals 1 to infinity of fn equals f almost everywhere, and the sum from n equals 1 to infinity of the integral of the absolute value of fn is finite. So you have almost everywhere convergence, and you have absolute summability. Then the sum of n equals 1 to infinity of fn equals f in L1 of R. Okay, and let me zoom out here and pause for a moment if people are still taking notes or have questions or comments or anything else. Again, this is sort of a restatement of what we already did before, right? So what we already did before, we started with the tilde equals, and then we upgraded the tilde equals to this statement just about absolute summability, and we're basically going to do it again here. The only difference is that here in this one we were given the function f, right? In the previous thing, we weren't given f. We were just given the fn's, and we cooked up our f over here. And then we're like, hey, the f we cooked up, like it works, and everything's fine. Over here, you gave me an f that was almost everywhere at the limit of the fn's. And like I have to prove not just that it's converging to something, but it's converging to the specific f that you gave me, right? And basically, the previous theorem says, okay, I don't know if they're converging to the f or not, but I know they're converging to that thing, whatever that thing is called. And that thing will be equal to your thing almost everywhere, and therefore they'll be the same thing in L1. This will be the kind of theorem we proved in the videos last time. So in other words, the proof is like this. I have to give it a different name now. We're going to let G be the function from corollary 2.5.4, right? So G is this guy. G of x equals, it's equal to the sum from n equals 1 to infinity of fn of x when the sum of the absolute values is finite. And it's 0 otherwise. Right? So the only difficulty, we know that these fn's are converging to the G, and we would like to show that it's converging to the f. And the thing is, the f and the g are equal almost everywhere. Okay? So we know, so by the corollary, right, let's continue this thought, such that G is sim equals to the sum from n equals 1 to infinity of fn. And this implies that G is the sum from n equals 1 to infinity of fn almost everywhere. Okay? So we have sim equals, and that definitely means almost everywhere equals. And in the actual statement of the problem, you gave me the f. You said there's some f, and then they're almost equal. And you have an almost everywhere equal function. I have an almost everywhere equal function. We've proven that almost everywhere obeys this kind of transitivity. So since the sum from n equals 1 to infinity of fn equals f almost everywhere, therefore f equals g almost everywhere. This actually, I think, even had a name. Let me see. Did I write down the name? Yeah, this was theorem 2.7.7. So it's the kind of thing you prove with those almost everywhere type things. This is the type of stuff we did in the last Thursday to Tuesday video. So f equals g almost everywhere. G is this thing. And we know, so we know from completeness of L1, or whatever theorem you want, that if G is sim equal to this Fn, then G equals the limit Fn equals 1 to infinity of Fn in L1. Right? That was the previous theorem we just did. So we proved that the Fn's, the sum of the Fn's is converging to G, but F equals G almost everywhere. And there's a theorem that says if F equals G almost everywhere, and G is converging to something in L1, then F is 2. Okay. This is, again, one of these almost everywhere things. So therefore, F equals the sum of n equals 1 to infinity of Fn in L1 of R as well. So since F equals G almost everywhere, therefore they have the same limit. This was also theorem 2.7.7. Yeah. Theorem 2.7.7 was this kind of thing. Okay, so that's basically it. Okay, so this is the kind of absolute summability condition that says that if you have almost everywhere convergence and you have this absolute summability, then it's all good and you have L1 convergence. Okay, questions or comments about that one? Yeah, it seems like we're not doing a lot in these theorems. We're just like pushing around definitions because we've done all the hard work already, right? Like we're just kind of clarifying what we're doing. And the big advantage of the way this is stated now is there's no sim equals anymore. The sim equals was really just to define the integral. When you start working on these things in real life, you never use the sim equals. And in fact, most textbooks don't define the sim equals at all. The sim equals was a special thing that this textbook did to avoid talking about the Lebesgue measure, which is some nasty thing. And so these are the types of theorems that if you ever take a different course, this is the kind of thing you'll use and the type of thing you'll prove. This is like the result that we need. Once you know the result, you don't need the sim equals anymore. Okay. All right. That is it for condition 1. So remember, condition 1 is saying, what do you need to add on to almost everywhere convergence to improve it to L1 convergence? And there's another type of condition. Condition 2, number 2. So Fn goes to F almost everywhere, and plus something is going to mean Fn goes to F in L1, and in L1. And we need something else. So absolute summability is one kind of thing we can have. Another kind of thing we can have is this condition. This is one we had kind of early on in the course. It's another kind of like, it's some kind of nice, Fn is not only going to F almost everywhere, but it's going to F almost everywhere in a, quote, nice way. Yeah.
Sorry, just to go back.
Yeah.
Like, how does the completeness of L1 imply that?
Yeah, what I mean is the proof we just did. Yeah. This is a good point. What I really mean is the proof over here. I don't know. Let's call this part by the, yeah. We know from the proof, let's say from the proof. I mean, I think this was a theorem, right? That if G is semi-equal to this stuff, then this works in L1. Like that really is the definition. Was it the previous thing we did? Ha! Okay, wait. Look, that was this theorem. Ha! Okay, I want this theorem. Okay, so let's replace this with that. From the completeness from previous theorem, and it was theorem 2.6.6. Right? Yeah, that was the theorem that gave us the completeness. I guess we did the completeness as kind of a side quest. Okay, yeah, no, good point. Thank you. Okay, back to this. Condition 2. So Fn goes to F almost everywhere, and it should be going in a nice way. What is a nice way it could be converging? Anyone have an idea? Yeah. Pointwise. Yeah. Well, almost everywhere is like pointwise light, right? Pointwise is everywhere. So almost everywhere is like pointwise, but relax it a bit. And then you need pointwise, but in a nice way. But what does a nice way mean? Another way to think about it is we've proven condition 1. Condition 1 says we have absolute summability. Absolute summability means that if you took all the things and you made them positive, it would still work. So what kind of conditions does absolute summability exclude? It excludes things that go up and down and up and down and up and down, right? If you're going up and down and up and down and up and down, then it could be that the final thing is like 0, because all the ups and downs cancel, but it's not absolutely summable, because if you take all the negatives and flip them upside down into positives, then they get really bad. So absolute summability is ruling out, it's saying, as long as it doesn't go up, down, up, down, up, down, up, down, up, down in a bad way, it'll be okay. And condition 2 is saying, as long as it doesn't go up, down, up, down, up, down in a bad way as well, but it says it by monotonicity. It's by monotonicity. Monotonicity. So as long as you have no downs, you're going up only, then this will imply that. Okay? And so the actual statement, and this statement has a cool name because it was some cool Italian guy. So this is the Beppo-Levi monotone convergence theorem. Monotone convergence theorem. Okay, and I'm going to give you one. There's lots of different, slightly different versions of it. But the one I'm going to give you goes like this. So if Fn are positive functions, so they have to start at 0, and then they go up, and weakly increasing. So that means 0 is less than f1 of x, is less than f2 of x, is less than ... So for all x. So the fn's, they go up, 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 and they eventually reach some function. And I'm going to call that function f. And f equals the limit as n goes to infinity of the fn of x. F of x. In some versions of the theorem, they won't give this thing a name. They'll say, if the fn's are going up and other conditions, then it's all fine, and you get an f. I'm telling you what the f is, because the other conditions, you just take what the f's have to go up to something, and we're just going to call that thing f. But in some versions, I'll write this, can also show f exists if it's not given to you. But I'm going to do the easy version. Okay. So f is the limit of the fn's. And there's one other condition we need. And the condition says the only thing that could go wrong here is if the integrals of the fn's, if they blow up to infinity, then we have no hope. But as long as the fn's are increasing up to f, and the integrals of the fn's themselves are bounded, then we're good. And there exists m such that, and I'm going to write it like this, the sup of n of the integral of fn is less than m. So the integrals of the fn's, they cannot pass m. M is like some upper bound that bounds the integral of all of the individual fn's. Okay, and the conclusion is then fn goes to f in L1. So f was defined to be the pointwise limit, and as long as the functions are increasing and their integral doesn't blow up, then the pointwise limit will also be the L1 limit. Okay, the proof is extremely simple because monotone is basically even better than absolute summability. If you're monotone, then you can turn it into an absolutely summable sequence. Absolutely summable means the absolute values add up. Monotone means the absolute values are always positive. So it's gonna work out really simply. So the proof is extremely simple. And all you gotta do is let Gn equal Fn minus Fn minus 1 so that Fn equals F1 plus the sum from m equals 1 to n of Gm. Okay, so in other words, the Fn's are the things that are converging, and you can write Fn as the sum of the G's. So we're going to look at this infinite sum of the G's. In fact, why don't I make F1 equal G1? F1 equals G1, because otherwise you can't, this is for n greater than or equal to 2, and then it really is just the sum. Fn equals this. So the Fn's are the sum of the G's, and now we're going to be in the setting, we're going to see if the Gn's are summable. We will see the Gn's are absolutely summable. Why are the Gn's absolutely summable? Actually, yeah, does anyone, can anyone see why the Gn's are absolutely summable? What can you say about the Gn's? Yeah.
Is it because they're like a telescoping sum?
They are a telescoping sum, but not only are they a telescoping sum, they're a telescoping sum given by these difference of the f's. And what do we know about the f's? Let's scroll up. What do we know about the f's?
Oh, it's always positive?
It's always positive. Very good. So because the f's are increasing, the g's are always positive. So notice Gn of x equals Fn of x minus Fn minus 1 of x is greater than or equal to 0 is given, and therefore the absolute value of Gn equals just Gn, right? So the Gn's are absolutely summable. That's the same thing as saying the Gn's are summable. The Gn's are summable because their sum equals f. So it's no problem. Okay, so the sum from m equals 1 to n of Gm in absolute value, let's do the integral of the absolute value. Well, the integral of the absolute value is just the integral. And now we're doing a finite sum of the integrals. That finite sum of the integrals is the integral of the finite sum. M equals 1 to n of Gm. And the sum of the Gm's equals the integral of the Fn. Right? So if you do the sum of the absolute values, you get the integral of the Fn, and that is bounded above by m less than m. So notice that this thing, by definition of m, by definition of capital M. So when you do sums of the g's, it's always less than m, and therefore the infinite limit is also less than m. The sum from m equals 1 to infinity of the integral of the gm is less than m, or less than or equal to m, which is less than infinity. Okay, and therefore the g's are absolutely summable. Therefore, the gm's are absolutely summable. And since they are absolutely summable, they converge to something. And therefore, the thing they converge to we already called f. So, okay, I'll go back and write that, but therefore, the sum from n equals 1 to infinity of gm converges in L1. And notice the limit must be f, because the limit as m goes to infinity of fm, that is what we called f, and that is also the limit of the gm's almost everywhere, by definition of f. So we called f the limit of the f's. F was the limit of the fm's, but the fm's are the same as the infinite sum of the g's, and so it's all good. Okay, that's it. So basically, the monotone convergence theorem is kind of a special case of the absolute summability where you're always going in one direction, and so like the absolute values just go away. So that's very, very nice. This is like a real theorem. If you take all sorts of courses, we'll do the monotone convergence theorem, and it's useful in a lot of places. Any questions or comments? Okay, the very last topic we are going to do in the whole of chapter 2, and then we are going to be done with Lebesgue integration, is condition 3. Condition 3. And condition 3 is also very useful. Condition 3 says if fn goes to f almost everywhere, and the conclusion is going to be that fn goes to f in L1, just like the other ones. And in condition 3, you have police functions. Police functions. You might say, what the hell is a police function? We're going to have some control. We're going to have some other functions that control the behavior of the fn. So the police functions are going to come and they're going to say, hey, fn, you cannot do anything bad, okay? And it's going to rule out exactly the kind of stuff we had way back at the beginning over here. So crazy functions like this, the police functions are going to control this kind of thing and say, hey, look, you can't do anything really bad. And if the police functions come along and say you can't do anything really bad, then we're going to have the same thing. That will be the topic of the video this weekend. So, and there's a very special name for this thing. It's called the Lebesgue dominated convergence theorem. LDCT is the Lebesgue dominated convergence theorem, which is the big theorem for this kind of thing that everybody uses all the time. So this is the kind of thing when you write like a math paper, you'll just say, by LDCT, blah, and you won't even cite anybody because like everybody's supposed to know the Lebesgue dominated convergence theorem. Okay, let's stop there, and I'll see everybody on Tuesday, and you'll have a video on this over the weekend.